Bonjour Bakary, Eddie Ginza, mon général, mon colonel.
All right, welcome guys. Let's try and see if we can do this within let's say less than 10 minutes. Okay, so this code is very, very long, and I just wanted us to share and try and understand how we can interface an LCD in Avr Assembly. All right, so it's assembly language that we are using here to try and program this microcontroller at Mega32 so that we can be able to interface or connect the LCD. All right, so quickly begin. I decided to prepare the code in advance because it's quite long and I wouldn't want to be making mistakes while we're making this video. So I prepared it in advance, ran it, and made sure that it was working well. All right, so I'll explain each and every line of code in this program so that not only are you going to have this code, but you are also going to actually understand whatever that is going on in this program. Okay, so you see, let me just align this here so that we'll be moving together. Okay, so guys, label. Okay, so we begin. So when we say include m32def.inc, we are basically doing here is we are just calling the library functions that has been defined already by the compiler to understand that what we are working with is actually at Mega32. All right, because in this Avr family there are actually a lot of microcontrollers. Okay, so when we say def, we are just defining or declaring this variable to take this. So the variable temp1, so we're just saying temporary one, is taking register 17. It's taking register 17. Then when we say .equ or .equal, what we actually mean is that we are actually meaning that we are defining the port. That's how you declare the port in assembly, Avr assembly, because assembly comes in different ways. There's assembly for PIC microcontrollers, and this is assembly for Avr and other microcontrollers that exist there, like STM32 and all those others. But now we are specifically looking at this one. So all this here, what we're just doing is we are giving the name and declaring to which port that is. So reset is connected to port C0. Write is connected to port C1, and the enable, which is actually the logic enable, is connected to port C2. Then when you say RJMP is unconditional, it does not satisfy it doesn't wait for any condition to be satisfied in order to jump. It just jumps. So RJMP init is unconditional jump to a specific label. So in this case, we are jumping to the label called init. There are other conditional jumps like branch if equal, branch if not equal. Those are conditional jumps, but this one is relative jump, which is not conditional. All right. So when you said dot, what you mean is just begin from address number. So here you are saying begin from this particular address 0 by 100, like that. Then we come to the label init. You see that we are setting the register temp to be high, and then we say out. So let's call this temp like that, not temp 1, because you see there's a mistake there. So we say set register temp. So we are setting it to high by means of saying set. We actually mean that we are loading ones into that. All right. Then we actually now whatever is happening here is we are just initializing what is going to happen when you power on our microcontroller. So you say output port C is an output port, DDRC is the data direction for that. Then you're also setting the port D is also an output port and its data direction. You can see that. So port D is set to be high, the status. Port C is also set to be high, the status, and also the data direction is set in that manner. All right. So now we come here now with the stack pointers. Why do we need the stack pointers? Stack pointer are very, very important because when you start using your delay command, you cannot work with delay command without these stack pointers. So these stack pointers helps you when you start calling your delay command. All right. So under this section, all what you are doing is that the LCD control port declaration, that's what you are doing here. You can even put a comment here if you want. This initialization section is where we are having our LCD port control, or LCD control ports are being declared there. All right. So after you begin, you load all those stuffs, then your main program will begin. So now the main program is here where you have got main here. So I'm rushing there because I know there's nothing really to waste much time on. So when you come here, you see that you are loading the temp with this particular address memory. Okay. Then you come and say out to ADCSR. So that ADCSR is just actually the analog digital converter. That is just your analog digital converter there. So when you load that, then you offload into here. Then again you load the temp with this memory location and you offload it in there. Again, now you call LCD. So when a call function calls a specific label, so in this case you call LCD, then again you call another label called message display, then you call another label called read from the analog digital converter. Then from there you come and say LDI temp. Again you load this memory address into the register temp, then you call some label called write. All right. Then again you load another memory location, which is this one. Then you call another label called write, and you call another label called pause. And then what you're doing here is now you're instructing how the LCD is going to be writing those characters on the screen and what interval will it be waiting. So we now come here. You see under here, what actually we have is the label called write. So on the label that we are calling write, what's happening under write is to say we call a pause. So after we call the pause, we are going to say LDI temp. You load this memory address into there. Then after you do that, you call write again, and then you call pause. So what's going to happen is after you have loaded that, you're going to write it. then you wait, then you load again, you write, you wait, then you load again, you write, then you wait, just like that. Then this return function rate means before you jumped to this label called core, okay, there is the way you are executing your code. So if you come back on top here where your core appeared, it appeared here. So when you code core and it jumped to that, it executed whatever was under that label LCD. Then when it finished executing what was on that label LCD, it will go back where it started. So it called LCD from here. So it jumped, it came to this LCD, it executed everything that was on LCD, everything until it reaches rate. When it reaches rate, it goes to where it ended before it jumped. So it came back here to again another core function, which is message display. So when it comes, it's going to call message display and it's going to jump to the label called message display. All right. So it will keep moving on like that. Then when it comes to some label called write, what you're going to move is that what you had in temp. I think I made a mistake on top here. Just give me a minute. Let me try and correct that. So we've got this temp one. Okay. So temp one is that, and then we just forgot to put one thing here, which is supposed to be okay. Just this. Let's just comment it out. Let's do this. Then we say def, sorry, we say dot def, so that we define that. Then we say temp, so we have defined that to be ARA16, so we have declared that there. Then now when we go back to our write, we are here, right? When we were here, if you remember, we ended here. So when we're at our write, we are going to move the contents that are in temp and move them into temp 1. So the register temp into register temp 1. Then you swap. The swap function just exchanges. Okay? The swap function just exchanges what you had in there into the other register, which in this case is temp 1. Okay? So after you do that, okay, so after you do that, so after you do the swap, then you call this is the list line, then you load it with temp, then you say and, just as like adding a 1 to that. So you see this, you add a 1 to the contents of temp 1, and after you add the 1 first, then you load it with the contents of this memory location. Then you load that into port D. Then after you load that into port D, you say temp. So you have loaded the contents of the memory of the register temp into port D. Then you say set a bit in port C enable. Okay. So after you do that, you call the S delay to wait. Then you clear the bit in port C, and again you enable. You call the delay, and then you call the return function where you ended before you jumped to the label called write. So if you come back here on top, if you come here, you see under your main, the first thing you called was the LCD. You went to that label. The second thing you called was the message display. Then you also called the write. So before you called write, just after you called write, what's the next thing that you called was pause. Then after that, it will keep on executing until it finds another core function, in this case again write. So it will be doing that repetitively because you'll be counting values. So as in the more you are counting the values, the more it demands for those values to be written to the screen. So that label will be actually executed repetitively. That's why you see we have got multiple core function for the write. So now you come to your data right here. So you move again in the same manner. You move what was in temp to register temp 1, then you swap. Okay? Then you do that from the list line. Then you do that. Then again you increment by 1 the memory location of temp 1 by 1. Then again you load that with the contents of this memory location here. Then you do that in the similar manner. Then you offload what is in temp 1 into port D. Then again you set the bit for port C. For reset, then again you clear the bit for port C to write. Then again you set the bit in port C, enable, just like that until you call the delay. So this will keep repeating. So now we come to the delay. So on the delay label, you have the no operation. So without doing anything, let me just get rid of that because it's going to give you an error, right? So it's like that. Okay. So we want this to happen twice. And you know the clock cycle for a NOP operation takes about 125 milliseconds, if I'm not mistaken. Then when it calls this delay, there will be no operation and no operation again, which means nothing will be done, but you keep on having a clock cycle without any instruction being executed. Then again you call the return function where was the execution line before it called the S delay. So it goes there, then again it comes back now to continue to delay section. So under delay section you push the contents of your R18. Then after you do that, you load 60 into your R18. Then you call your loop 1. So under loop 1 you call your delay, S delay. You decrement the contents of R18. You keep on decrementing until it gets 0. If it's not equal to 0, you branch again back. If it's not equal to 0, you branch again back to loop 1. If it's equal to 0, you proceed with the operation R18, then you call the function return so that you continue from where you jumped before you called the label delay. Then you pause. Under the pause label, you push the contents of R18, then you load. After you load 20 into, so what you're doing is that when you be counting, as you be moving your potentiometer, it will be moving like 20, under 20% what's happening, under 60% what's happening, until you keep on going like that. So then you come to loop 2. So this can give you an error. So when you come to loop 2, you call the delay, you decrement R18, you branch. So you keep on decrementing, okay? You keep on decrementing like we did in the timer timing without a timer. So why you're doing this is you're having that much time for the delay that is required, which is in this case the 2 millisecond function. All right. So you load it with a 20. Okay. So this 20 that you load into there will keep on decrementing until it reaches 0. For as long as it's not equal to 0, this is why you see we have got a conditional branch statement here, which is saying branch if not equal back to loop 2. So for as long as it's not equal to 0, it will go back there until it comes 0. When it comes to 0, then it will proceed. Then you call the return function. Then after we call the return function, then we go back to where we ended before we called the loop, before we jumped to loop. All right. Then this will continue now to message display. So under the message display, you are going to write the following like that. So your message basically here is just numbers counting from 0 to 255. So you see now, in order for you to do that, now you are calling the you are calling the high RAM end, or you are calling the stack pointer Z, the high side of the stack pointer Z to display the message, and the lower stack pointer End to display that message, and then you call the loop. Then you keep on incrementing. After you increment the contents of the Z register, then you load it. After you increment it, then you load it into the register temp. Then you say compare immediate with 0, and what's the content of the temp? Is it at 0? If it's at 0, branch if equal, then you say stop. Stop if Z plus contains a 0. If it doesn't contain a 0, you keep on counting. You keep on counting like that. So then you now call the function data write, then rjmp loop. So under the label stop, the only thing that's appearing there is just to return to where you ended before you code it. Okay? And if you can see, where you ended before you code it was the core function data write. Then again, we now come and write the message. So how do you display the message now on the screen? On the screen you said dot database, then under your dot database you put these two, you say meter read, then you put that, then you say comma 0. So it means that it will be beginning at 0. Then you begin at memory location 500, because you know that this can hold the 256. So now you say read ADC. So under read ADC label, this is where you're going to say, you set the bit. So after you do this is ADC start conversion to keep polling or keep counting if you want. You keep, because there should be a conversion that's happening. All right. So now you say in, you know what an in command does. Then you load this into R20, because here you cannot use an LDI to load into there. You can't load immediate. So in this means like you read the contents of ADCSRA. So then when you do that, you come here, you say SBRS command R20 add if check the analog digital conversion interrupt flag, or you jump to keep polling. Repeat if not set until you clear ADC interrupt flag by checking the in temp. Okay? And you read the analog digital, the lower nibble there. Then you call the ADC conversion again. Then you come to move temp into there. So by this means you just copy the contents of R2 into temp. You see, R2 does not work with LDI command, but it works with move. So the only way you can exchange the content or transfer the contents of register 2 into temp is by using a move command. Then you move again R1 in the similar manner. Then you call data write label. Then you move the contents of R0 into there. Then you call again data write. Then you say LDI temp. Then you load this memory location into there, and then you call, and then you say call write to do the write function or the write command there. Then you load the content of this memory location, and then you call the label write again. Then you load the content of read memory location, and again you do the similar thing, and you do that until you jump to the label called read ADC. So under the read ADC, what you're going to have is that you shift the cursor position to left command right function, you shift again, you copy the content of that and everything, and then you shift cursor position to the left. So sorry for that. Okay, so we are here. So after you do that shifting, then you come to ADC conversion, because there should be conversion that should be done between the ASCII values that you're supposed to, the decimal value that you're supposed to show on the screen, and the signal that you're feeding by means of a potentiometer. All right. So you move now the contents of temp 1 to register 0. Then you move this. Then again you say BRLO command here, branch if lower. That is to say 0 by 64 here, then subtract immediate the temp or the register content of subtract immediate the register contents of the contents of this memory location. Okay, so in this case, I think we made a mistake there, sorry for that. Okay, so then you increment that. So that was a mistake, sorry, just made a mistake there. Okay, so under there, then you do your immediate subtraction. So you subtract, this is your destination, so you subtract this from the contents of that. Then you increment R2, you compare with the contents between this and that, which is between the register temp and the memory location 64. Then you call the brush command there. Then you jump to some label called here 1. So under that label, what you're going to do is that you compare this memory location with what is, so here you are comparing with this memory location and the contents of temp. So you branch if lower. So now we branch to where? To here 2. So under here 2 you subtract immediate. Okay? You subtract immediate the contents of temp and the contents of this memory location here, and then you increment, you subtract this from there, and then you increment the contents of R1. Then after you do that, you call a brush here, which is branch if same or high to here. This means that branch if same or high to some label called here 2, and which is there. Then you see again we come to some label here 3. Under the label here 3, what we actually have is you move the contents of temp to R0, move into R0, then you load this memory location into temp 1. Then you do the OR command. Okay, OR command. OR command is just like addition, or sometimes we call it bitwise, or between registers, or between registers R1 and temp 1. Then you call the rate where you ended, and this will keep on repeating like that, and your code would have finished just like that. So guys, this is how you can interface the LCD to the Atmega 32 AVR microcontroller in assembly language. I was using Crossworks, but this same code can run in Atmel Studio. So take your time, go through this, and have it working. Alright? If you have any question, please don't hesitate to leave a comment. Okay. Thank you so much.